Hello, I'm Tom Nahumi from Dell EMC. In this demonstration video, I'll be showing the Dell EMC PowerFlex CSI driver features and installation methods. Before we get into the CSI components, let's quickly review the PowerFlex building blocks to get a better understanding of the system. PowerFlex fundamentally consists of three types of software components: the storage data server, the storage data client, and the metadata manager. The storage data server is installed on every node that will contribute its storage to the system. It owns a contributing drive and together with the other SDSs forms a protected mesh from which storage pools are created. The MDM hands out instructions to each SDC and SDS about its role and how to play it, giving each component all the information it needs. The storage data client allows an operating system or hypervisor to access data served by PowerFlex clusters. The SDC is a client-side software component that can run natively on multiple operating systems and is optimized to use multiple networks and endpoints in parallel. The first step is installing the driver. In the latest release, CSI 1.3, we've added support for OpenShift 4.5 and 4.6 with RHEL and CoreOS worker nodes. This means that from now on, we can automate the SDC deployment on OpenShift CoreOS nodes, and since it runs as a container, no component is installed on the operating system, and the CSI handles the whole deployment process. I will be using the Helm installation method for this deployment. As you can see, I installed a new OpenShift 4.6 cluster. By navigating to the Compute tab, we can see that the worker nodes are running RedHat CoreOS. By default, OpenShift runs on CoreOS, which is a fully mutable operating system that is delivered and installed as a component of OpenShift. And as a result, until now, it wasn't possible to install the PowerFlex SDC component on CoreOS worker nodes, and RHEL compute nodes were required to deploy and use the PowerFlex CSI driver. Starting from OpenShift 4.6, the strategy of bring your own RHEL nodes is now deprecated, and support for using RHEL compute machines is planned for removal in a future release of OpenShift 4. One of the highlights of this CSI release is the SDC init container. We've made an architectural change in the driver during the CSI installation, and now it automatically deploys the SDC component as a container on each CoreOS compute node, so that users can now use CoreOS compute nodes to consume storage from PowerFlex clusters using the new CSI driver. With that, let's install the new PowerFlex CSI 1.3 driver. The first step is pulling the latest driver from the official GitHub page. Then, we need to create a new namespace for the driver. As part of the installation, we need to create a secret file for the PowerFlex credentials. The values are encoded with base64. The next file we need to create is the values file. Here, we specify the PowerFlex details such as system name, gateway IP, storage pool, and MDM IPs. Now, I'm running the installation script. I'm specifying the namespace and the values file I created earlier, and I'm also specifying the snapshots flag to enable snapshots functionality. The installation script is running verification steps and deploying the CSI controller and CSI nodes on each OpenShift compute node, as well as the required sidecar containers using Helm. If we navigate to the OpenShift UI, we can see that the CSI driver pods are now initializing. In addition to the driver and registrar pods, we have an additional new init container, which is used to run the SDC on that node. As you can see, within a few seconds, the driver is up and running, and this means that the SDC component is functioning and can access data served by the PowerFlex clusters. As you can see, there are currently no PVCs in my cluster. By navigating to the Storage tab, we can see the new VxFlex storage classes that have been created. Now, let's create a new PVC from the PowerFlex storage class. I set the storage class to VxFlexOS and the size to 32 gigs. As you can see, the volume hasn't been created yet, as the volume binding mode is set to wait for first consumer. This feature was added in CSI 1.2 in order to provide topology awareness. So now, let's create a new demo pod with a claim for that PVC. As you can see, as soon as Kubernetes is receiving the request, a new volume is being created and mapped to the worker nodes running this pod, using the PowerFlex CSI driver. If we navigate to the PowerFlex UI, we can see that a new volume representing the persistent volume has been created and mapped to the OpenShift CoreOS compute node. In order to automate and simplify the CSI driver installations on OpenShift clusters, we've developed the Dell CSI operator. This is a Kubernetes native application which helps in installing and managing CSI drivers provided by Dell EMC for its various storage platforms. Dell CSI operator uses Kubernetes custom resource definitions to define a manifest that describes the deployment specification for each driver to be deployed. Multiple CSI drivers provided by Dell EMC and multiple instances of each driver can be deployed by the operator by defining the manifest for each deployment. In order to start using it, all you need to do is navigate to the Operator Hub, search for the Dell operator, and click on Install. From the OpenShift console, we click on Installed Operators and then on the Dell CSI operator. Here, we can see a list of all the available CSI drivers we can deploy using this operator. We go to the VxFlexOS box and click on New Instance. Here, we need to specify the relevant details about our environment before installing the driver. Under the system name, we enter the system name or ID of our PowerFlex cluster. Under the endpoint, we enter the address of our PowerFlex gateway. We set the Enable Snapshot Creation and Deletion parameters to True. This feature is supported from OpenShift version 4.4 and above. Next, we edit the values of the default storage classes. We enter the system name and the pool name. In case we have multiple storage pools, we can create a dedicated storage class for each pool. As you can see, the volume expansion parameter is set to True by default. Now, we click Create to install the driver. Within a few seconds, our driver is up and running. By navigating to the Pods tab, we can see the VxFlex controller as well as the VxFlex node pods which are installed on each of the OpenShift worker nodes. It is important to note that the SDC driver should be installed on each worker node prior to the CSI driver installation. We can also see that new storage classes have been created, and now we're ready to discover the new features. The first feature is Topology Support. The PowerFlex driver version 1.2 adds support for topology, which forces volumes to be placed on worker nodes that have connectivity to the backend storage. This covers use cases where the PowerFlex SDC may not be installed or running on some nodes, or where users have chosen to restrict nodes on which the CSI driver is deployed. In order to utilize the topology feature, the storage classes are modified to specify the volume binding mode as wait for first consumer, and to specify the desired topology labels within the allowed topologies. This ensures that the pod scheduling takes advantages of the topology and be guaranteed that the node selected has access to the provisioned volumes. Now, I'm going to create a new PVC from this storage class. As you can see, the operation completed successfully, but the PVC status is pending. By running the kubectl describe command, we can see that the CSI driver is waiting for the first consumer to be created. Now, let's create the pod with a claim for this volume and see what happens. As you can see, as soon as the pod is created, the CSI driver created a volume and mapped it to the specific worker node where this pod is provisioned on. The PVC status has changed to bound and the pod is up and running now, connected to the requested persistent volume claim. By navigating to the PowerFlex UI, we can see that the volume has been created at the storage array level and mapped to the OpenShift worker node. The next feature I would like to show you is volume expansion. Starting from version 1.2, the CSI driver supports expansion of persistent volumes. This expansion is done online, that is, when PVC is attached to a node and the pod is running. In order to use this feature, the storage class used to create the PVC needs to have the attribute allow volume expansion set to true, as I showed you during the CSI installation. The PVC I created in the previous example is bound to the pod. In order to expand the volume, all we need to do is run the kubectl edit PVC command and specify the relevant PVC. Then go to the storage parameter, change it, and save the file. In the background, you can see the immediate change at the storage level. It takes a few seconds for the persistent volume and persistent volume claim to get updated as well. Volume Snapshot feature in Kubernetes has moved to beta in Kubernetes version 1.17. It was an alpha feature in early releases. This feature allows you to create multiple copies of your persistent volume, whether the use case is backup and protection, or additional copies for test and dev clusters. In PowerFlex, snapshots are block image in the form of a storage volume used to instantaneously capture a state of a volume at a specific point in time. PowerFlex snapshots are fin provisioned and writable, and once the snapshot is taken, it becomes a new, unmapped volume in the system. Similar to the storage class, in Kubernetes we have an object called volume snapshot class. I created a snapshot YAML file called snap1 and set the source of the volume to be the PVC I created in the previous demo. I'm creating it using the kubectl command, and if I navigate to the PowerFlex UI, we can see that a new unmapped snapshot has been created from our existing volume. At this stage, we can create multiple copies of this snapshot and connect them to additional pods. In this YAML file, I set the PVC data source to be the snapshot we've just created, and set the size to be the same as the original persistent volume claim. By running it using the kubectl command, we can see that a new read-write volume has been created from the snapshot, and we can map it to new or existing Kubernetes pods. The last feature is raw block devices. The PowerFlex driver version 1.2 adds a support for raw block volumes, which are created using the volume devices list in the pod template spec, with each entry accessing a volume claim template specifying a volume mode equals to block. Raw device volumes are presented as a block device to a pod by using a bind mount to a block device in the node's file system. There are some specialized applications that require direct access to a block device because, for example, the file system layer introduces unneeded overhead. The most common use case is databases, which prefer to organize their data directly on the underlying storage. In this example, I'm creating a new persistent volume claim called block PVC, and the volume type is set to block. In addition, I'm about to create a new pod, and the raw block device will be mounted as /dev/xvda once the pod is up. I'm creating them using the kubectl create command and waiting for the pod to start. By navigating to the OpenShift UI and selecting the new pod I've just created, we can open a terminal to the pod and verify that the new device is mapped to the pod as a raw device. The last feature I would like to cover is volume cloning. The PowerFlex CSI driver supports volume cloning. This allows specifying existing PVCs in the data source field to indicate the user would like to clone a volume. A clone is defined as a duplicate of an existing Kubernetes volume that can be consumed as any standard volume would be. The only difference is that upon provisioning, rather than creating a new empty volume, the PowerFlex creates a read-write snapshot which is exact duplicate of the specified volume. The source PVC must be bound and available. Source and destination PVCs must be in the same namespace and have the same storage class. To clone a volume, we need to specify the source volume under the data source parameter. And of course, the size and the storage class name must be the same as the original volume. Again, this volume won't be provisioned until we create a new pod. So let's create another pod with a claim for this volume. As you can see, both PVCs are bound and the new pods are now up and running. If we go to the PowerFlex UI and click on the source volume, we can now see that a new read-write snapshot has been created, which is basically our new Kubernetes persistent volume. Starting from OpenShift 4.6, volume snapshot views have been added to the UI as a tech preview, so now, in addition to the OpenShift storage objects, we can view, edit, and create volume snapshots directly from the UI. I really hope you find this demo useful, and thank you very much for watching.